Thank you, Jose. As in every TV series, you want to know what happened in the last episode. And the last episode, 11 years ago, Wilfried Stöcklein presented his work on the forensic analysis of float glass, which was mainly focused on the characterization of glasses from international sources. And I just repeat what he said, or recall it, what he said 11 years ago. Well, at the BKA group, there was a big sample collection of float glasses of international origin. 61 glasses were analyzed by elemental analysis. The main focus was on ICP-MS, but also XRF methods were used. Also, the refractive index was analyzed. These glasses were, the composition was there, you see, the distribution. Half of them were from Europe, a third from the States, a couple of Japan. So at that time, there were about 160 float glass plants around the world, and maybe 80 plants in the so-called Western world. So we thought we got a good representation at that time. Different colors, different producers. The main focus of the work was liquid digestion ICP-MS work. I won't go too much into detail because we got two excellent presentations, one from Jose and one from Karen, representing doing the work. So it's time consuming. You need some material. The material is left over, so it's dirty and takes time. The results he presented 11 years ago was that it showed a limited discrimination power of refractive index, or the use of the results of the refractive index measurements by itself. So 10% of the glasses were indistinguishable by refractive index. You got a full differentiation of all glasses by application of ICP-MS, measuring 30 elements. And out of this whole set of elements, there was a selection made by chemometrics, which are the most discriminable elements which have the highest discrimination power. And then also a characterization of glass origin was tried to be established. So the conclusion was that quantitative analysis of 30 elements by ICP-MS improves the evidential value of glass examination. So I will talk about laser ablation. You've seen this before. Laser ablation, what it is, I won't repeat it. You ablate material, it's being transported in the plasma, and this is our old chamber there. You can see easily, this is the introduction of the carrier gas, and then it goes to the ICP. The new laser ablation systems, you can't take really good pictures because everything is encapsulated. Okay, the old stuff, it was always a little more hands-on. Yeah, the stuff gets transported into the plasma, ionized, atomized, ionized, and then you have a mass spec. Also, this one was presented in a very good way yesterday by Karen. The advantages of laser ablation, you can measure on very small samples, no sample preparation time, and, well, you see it has many advantages. The history of the instrumentation regarding elemental analysis on glass was in our laboratory that we use ICP-MS since the early 90s. In 96, we purchased a UV laser ablation system, which was really not that good. And actually, at the moment when infrared laser ablation system was not affordable, but on the market, we exchanged the system, the UV one by the infrared laser, and then in 2003, the whole system got replaced. So we were using this system as it is shown on the slide since '97. It's a quadruple ICP-MS system, and on the other hand, it's a VG laser system, and we had lots of problems with this machine, or I should say we gained lots of experience during using this laser for 5 years. The main thing, I won't bore you with too much details, but it was a problem of stability. The signal stability was not there. The intensity dropped down after a while. At first, of course, you think it's the mass spectrometer. It was not the mass spectrometer. It was the laser ablation system. And what it was, okay, we thought, okay, it's a temperature issue. So we installed a cooler, a water cooler here with a vent on it to get a stable thermal system here. This helped a little bit, but the whole problem was the laser head, which is here. So to gain good sensitivity and get stability on a daily basis, you had to fine-tune the laser crystals on a daily basis, which, if you tune your laser on an everyday basis, you get experience at this, and, well, then it works. With the new system, you don't have these problems anymore. It's just working fine. And we don't have any complaints with our new system, which is the standard apparatus used also in other places. So, okay, now the instrumentation is set, the system is working fine. Usually when you do elemental analysis on solids, by laser ablation, you need a standard material. And as a calibration standard, usually the NIST 610 or NIST 612 in this case is used generally. And we said, okay, we are not satisfied with this standard material. We think we should get better results if we have a calibration standard which has the same matrix, so the composition of the main and minor elements is the same, and the concentration of the elements which we think are interested should be in the same range, which is both not given by the NIST standard. So we came up, we talked to the people of Shot Glass, which is a German glass producer, and it was a small research and development project, and we defined our needs, and they produced 2 standards for us. It took in total 3.5 years. More than 1 year was only the contracting between the lawyers of BKA and Shot Glass getting agreed on a common idea, and okay, and then after a while we got these glasses, which are glasses which has a float glass composition, but they are not float glass, they are not industrial made glasses, so they don't have a float side, and we've prepared them, so now we have discs like a typical NIST series. Then a very important step which brought us, which really helped us a lot, was the Night Crime network. It was a European Union network project in this time, and our main focus there was on float glass because we thought it's the highest of forensic interest. Within the network, a protocol was established, and also the network was used to evaluate these new calibration standards. I'll just focus on 2 work packages. The first one was the instrumental validation, which was the first thing we did within this project, which was led by the ETH Zurich, Detlef Günther and Christopher Latkosi from the ETH laboratory, where 2 interlaboratory tests were carried out. And then in the second work package, which the coordinator was the BKA, we focused then on float glass, and also two another tests were rounds of tests were carried out. So in total, we had 4 interlaboratory tests and 3 tests with a similar setup. We had totally different laser ablation systems or combinations of quadrupole ICP-MS and 1 sector field system with different kinds of lasers. So you see there's a quite variety of instrumentations. These were the institutes which were, or laboratories which were very active and who gained or granted the success, because without the good data out of this project, you don't get any success. So the results, I won't bore you with any data or of this network, was that you can get really good data. You get good data. It's a reliable technique, even though used completely different instrumental combinations, and yeah, the locations were worldwide. And so this work was done for embedded glass, not for fragments, but it was results we gained for float glass, not for standard material. So we proved there's a good method using a protocol which was refined over the years. And this protocol also, of course, improved the precision and accuracy of the standards. And we use these new materials also as calibration standards, and of course they can also be used as external standards or for tuning standards. And this work was published 2 years ago. So now we have a system, we have a protocol which is working fine, And so what we did is we just reanalyzed all the glasses which were in our collection at that time to see, do we really get the same results by laser ablation as we did by liquid ICP-MS, by our standard method. This is, maybe you've seen it in a workshop before, typical laser crater. It's a microscopic image of a crater, so no SEM picture as usually, and it's in the same dimension as the diameter of a hair. And these are some results. These are box Whisker plots. So it's a logarithmic scale. What you see is the distribution of the elemental concentration of all 63 glasses. So you can see it's like minimum and maximum and outliers. And now I can use the median because I learned what it is, so I'm quite glad I learned it at this meeting. Anyhow, as you see, for the main elements, the variation on a logarithmic scale is not that high, not as high as you see for aluminium and potassium. Also for other minor and trace elements, you have a much better variation. So the discrimination power concerning this data set of 63 flow classes from global origin is much higher for like these minor and trace elements. But certainly I don't want to say that people who are, for example, using SEM shouldn't give it a chance differentiating glass, because even if you have a more limited chance in discriminating stuff, because with your sensitivity mainly focused at the minor and main elements, the discrimination power is not that bad and not that good, but still you can do something about it and you get results out of it. So this was the variation. What we also did is, for example, this is a plot the potassium concentration against the aluminium concentration, and there are two things you can see. One thing is that the data or the elements which we are measuring there, they are not uncorrelated. So there's a high correlation between potassium and aluminium, as you see. And then again, what you also see is that there are kind of groups. There's like Japanese glass tend to have very high potassium or higher to aluminium concentration than, for example, American glass. But of course, there are overlaps, and the more data you have, the bigger your clouds are getting. So then we had a couple of cases quite recently where we had a couple of burnt cars, and there was like melted glass, and the question was, is this glass which we found close to the car from the car, or was it a bottle glass with some liquid in it or so? So we did a couple of measurements. So we already had our data set with the float glasses. Then we got container glasses from 20 different German bottle manufacturers and just gave it a chance. And here you see also, I just selected a couple of elements. It's potassium, calcium, titanium, and manganese. The first one, on the left-hand side, you always see the distribution for the elemental concentration distribution for float glass, and on the right-hand side, it's for container glass. So in these cases, you see there's a trend that the concentration of these selected elements in container glass is higher than in float glass. And well, we figured out that still you can say that at calcium here that they don't, they're separated, but in a way you don't know. Maybe if you measure 200 instead of 20, then there is an overlap. So therefore, we looked for other ways of showing without doing PCA, which we did, but in a way to make it easy, we just printed the lead against the calcium to magnesium ratio. And there you can see what we got. There's the container glass and the flow glass, so we are quite satisfied with this. We will carry on with, of course, more data and more glasses. But for the time being, we thought it's fine. So, okay, what else can we do? Analysis of small fragments. This work also, Jose talked about it. We did it also. We got a couple of fragments. We quantified material, and here you see a fragment which has a size of approximately 1 millimeter or even a little more, and 4 spots on it. This is a typical spectra here. So you integrate You have, in this case, 30 seconds of integration time. This is a much smaller fragment. As you see, the weight is almost 200 micrograms. And out of these 4 spots, you see at least 3 spots went through. And it's quite easy to see that these 3 went through the material, and this one didn't make it. And then, OK, you see what you see. Of course, you have a drastic decrease of signal because you are ablating the sticky tape below it, and of course your integration time is pretty much reduced. And then for an even smaller, like tiny fragment which only has a weight of 17 microgram, then you can make two drillings, and then the whole material is just cracked and blasted away by the helium or argon stream. So then you have an integration time only of 5 seconds. Okay, and then we compared the results we got out of these different shots. We did it even for more fragments just to shorten it. And we saw that the mean concentrations we got out of it, they were all the same. So they don't change. The only thing which changed was the standard deviations, of course, for the elements. And by, for example, excluding the suckiest measurements, to put it this way, like the smallest ablation, to be more scientific, just by removing it, we can increase or we can decrease the standard deviation for the elements, depends on the element, by 0.1 to 1.5%. So the accuracy seems to be okay. It's just the standard deviation which changed. So this was one thing. You can do it on smaller fragments, but you have to be careful and really know what you're doing. The next step, I want to talk about how laser ablation changed our approach in casework. And as it was said before, good science always starts with good microscopy. The first step is, of course, the physical examinations, so the microscopy. And this is not changing, even if you have laser ablation ICP-MS. But then, this is as we did it in the past. We carried out refractive index measurements, and if the refractive index was indistinguishable, we then carried out further elemental analysis. Due to the fact that laser ablation is quite fast and not as time-consuming, I mean, I can only talk about my lab as refractive index. We sometimes reverse the order, and we use the laser ablation ICP-MS as a screening technique. And then later on, we do refractive index work. So these techniques is really changing a lot. Okay, yes. When you do so, which tend to happen, then you have to be careful, because by ablating material out of your glass and penetrating the glass, then certainly the refractive index can be changed. So if you have only a very small piece, you ablate it and then you give the rest to the refractive index people, you can really screw up. And we did a couple of experiments on this. You should know that this is upside down. So this is the surface of a glass fragment. So the laser was penetrating through here and drilling a hole which got bigger and bigger and bigger until here. So this is, in a way, a side view of a laser crater. And the normal or the refractive index of this material without any thermal treatment, to put it this way, you see down there, it's so 27 to the power of -5. And well, you see certainly some changes around these areas caused by the interaction of the laser. And yeah, this is about 90 to 100 micrometer, and it's about 70 micrometer, just to give you an idea about the size. So something is happening there. We carried out a homogeneity study. The FBI and the FBI carried out a homogeneity study, and they were so nice to give us the samples. They carried out GRIM and ICP-OAS measurements, and we carried out laser ablation ICP-MS work. And this was the sheet, and we analyzed 44 of these samples. And what we got out of what the FBI got out of the homogeneity study was that for the refractive index, the glass was quite homogeneous, so there was no trend diagonal or at the side, and also ICP-OAS had very small standard deviations, and there were no big trends within the sheet. For our laser ablation ICP-MS, we also did a measurement of 44 samples. These are the standard deviations we got for the elements. And we also carried out a couple of more analyses. So we analyzed smaller areas of the sample. So we got the variation within one part, we got the variation over the pane, and then we reanalyzed one and the same sample 10 or 12 or 13 times for every data set. So we also got over the ANOVA analysis, we got some analysis of variance. And there we could see that there are significant influence of sample inhomogeneities for a couple of elements, for other elements not. And these elements which were really touched by the homogeneity of this pane was aluminum, zirconium, hafnium, and lead. And so there we are pretty close to the micro heterogeneity of the glass. So if you then decrease your crater size, then certainly you have a problem. I'll just talk a second about the match criteria. You don't want to run into these problems of false exclusion or false inclusion. And so what are the possible match criteria on the market, to put it this way? One is the Hotelling T-square test. And this test requires more measurements than elements. So for us, it's impractical. So if on a routine basis with our protocol, we would like to have a knowledge on 20 elements. So carrying out 21 repeats is not really, on each fragment is really not practical. We usually do 6 repeats. T-test is advocated. We realized that you have much too many type 1 errors because the precision of the machine is too good. So therefore, it's not practical. PCA is also being advocated. I stated it here. We don't advise using it, or we don't use it for ourselves because it's a relative technique. Certain things of drift correction can't be taken into account, so we don't like it. And the N-sigma criteria, we think it's the best. So this is just a pairwise comparison of different data sets that for us to say, okay, because wherever you say your match criteria is, it's always a compromise. And in our case, we said, okay, we will carry out measurements or take as a match criteria 4,0. So it means 4 sigma between the two classes which are compared, and no element will be excluded. Like if one is excluded, then it's certainly different. And this is right now based on the data sets we have for like this BK FBI glass study and our other studies where we did a pairwise comparison of glasses of different origin. To sum it up, we introduced a new matrix match standard for glass analysis. We had this night crime activity, which was very successful, and we have a protocol which I think works fine. We had the collaboration with the FBI, which is still ongoing. Now we will analyze in the near future other glasses, also looking more, having a closer look on variation of glass. We have the reanalysis of our data set. We have optimized match criteria now. We had carried a lot of more validation work, or we had to do it because this method got ISO 17025 accreditation just in May of this year. And it has been applied, or it's applied routinely in every casework. And even if the sample is too small to get analyzed, the recovered samples, then we just measure the control samples. So in every case, we are using this machine. And I'm really sometimes, I'm really afraid of what we did in the past, because in one case, it's a case which happened about 4 weeks ago. We had 3 recovered glasses and one control glass, or control glass, you say? Yeah, control glass, which had the same refractive index. So there were 4 glasses, and we handed them over to the laser ablation ICP-MS people. They measured it, and there were 4 different sources. So it's really crazy in how many cases now we really get different results for glasses where in the past we said it's indistinguishable by refractive index. So I would like to thank Maureen Bottrell, Jody Webb, Bob Kuhns from the FBI for the good cooperation within this last studies we undertook. Of course, Peter Weiss, who is the glass examiner in our group now, and Mark Dücking, the engineer, and Peter Watzke, 2 engineers who are really trying hard at the ICP that we don't have any day without the plasma on. And I would like to thank also all Night Crime members for the support and the good work we carried out. Oh, and down there, I did acknowledge too many people. It's Annette Walter from Schott AG for the good cooperation of producing the standard. And of course, I would like to thank you for your attention.